One type of galaxy is the Milky Way, and the galaxy that is closest to us is the Andromeda Galaxy. We believe there are approximately 100 billion galaxies in the visible universe. The Andromeda Galaxy has played a crucial role in shaping our comprehension of the cosmos and our position within it. This discovery provided persuasive evidence that the universe does not revolve around the Milky Way. It proved that the notion that the Milky Way was the only galaxy in existence was incorrect, implying that we are merely a tiny fraction of the vast universe in which we live. Our knowledge about Andromeda has grown over the previous century, mainly through observations made in space. But with tools like the James Webb Space Telescope, JWST, now at our disposal, our perspective has changed significantly. Unexpectedly, recent information from the JWST has challenged our previous notions concerning the presentation of another cosmic puzzle, the Andromeda Galaxy. The JWST has received strange messages from our neighboring galaxy that have left the scientific community amazed. Join us as we look into how the development of the Andromeda Galaxy has shaped our understanding of the Milky Way. People's perceptions of the Milky Way have changed significantly throughout history, influenced by our advancing understanding of the cosmos. In the past, when technology was limited, the Milky Way appeared as a hazy ring of light that spanned the night sky, evoking a wide range of meanings and mythologies. It was often seen as a mystical and essential component of the cosmological beliefs of different cultures. In the 1920s, American astronomer Edwin Hubble made a transformative discovery through the Hooker telescope on Mount Wilson. His observations and analysis revealed that distant nebulae beyond the Milky Way were distinct galaxies, each containing billions of stars. One of the closest of these galaxies was the Andromeda Galaxy, also known as M31. Andromeda has a long and varied history, with observations dating back centuries. One of the earliest documented accounts of this celestial object dates to the Persian Empire in the 10th century. The astronomer Abdul al-Rahman al-Sufi described it as a small cloud in star charts from that period. These observations are significant in the capacity al-Sufi possessed to locate this cosmic entity far away, without the assistance of telescopic instruments, relying solely on his keen perception and observations. In 1612, a more detailed description of the Andromeda Galaxy, based on telescopic observations, was provided by Simon Marius. His work laid the foundation for future astronomers to study this massive cosmic structure. The renowned French astronomer Charles Messier assigned the Andromeda Galaxy the designation M31 in his well-known Messier catalogue in 1764, although he incorrectly claimed its discovery despite Simon Marius being aware of earlier records. Still, Messier contributed significantly to bringing more attention to Andromeda, and for almost 100 years after this, astronomers around the world worked to gather more information about this enigmatic galaxy, each building on the findings of their predecessors. Before these discoveries, the Italian astronomer Galileo Galilei revolutionized our understanding of the Milky Way in the early 17th century. Using his newly developed telescope, he made groundbreaking findings that challenged the prevailing Aristotelian cosmology. He discovered that the Milky Way was not just a diffuse band of light but a massive collection of individual stars, planets, and other celestial objects. Through his observations, he showed that the Milky Way was not at the center of the universe, as previously believed, but instead a vast expanse of stars scattered across space. In 1750, English astronomer Thomas Wright put forth a novel hypothesis about the universe. He speculated that the Milky Way was not just an accident, despite the distribution of stars. Instead, it was a structured flat layer. Additionally, he suggested that a portion of this vast structure contained our own solar system. While Wright's hypothesis was an improvement in understanding the structure of the Milky Way, it remained constrained by the limited observational technology of the time. At that time, most still believed that the Milky Way was the entirety of the universe, a belief that, considering the limitations of technology, was not entirely accurate. A significant rise in understanding the nature of the Andromeda Galaxy came in 1864, when William Huggins, an English astronomer, made an innovative observation. He investigated the spectrum of Andromeda and discovered that it was distinct from the typical gaseous nebulae. This discovery paved the way for scientists to comprehend Andromeda for what it truly is, a galaxy. Understanding Andromeda today, the mass of Andromeda is estimated to be between 1 and 2 trillion times that of our Sun, making it an enormous cosmic structure that happens to be in close proximity to us in the vastness of space. Based on research conducted so far, scientists believe Andromeda is about 10 billion years old. Its ancient age hints at a long and complex formation history and evolution. One of the most interesting hypotheses about Andromeda's origin suggests that it formed through the merging of several smaller protogalaxies over billions of years. This theory implies that smaller galactic entities merged gradually under the force of gravity to form the majestic Andromeda Galaxy we see today. Galactic mergers are common occurrences in the universe and play a crucial role in determining the structure and growth of galaxies. For a long time, astronomers believed Andromeda was significantly more massive than our own Milky Way galaxy. From Earth's vantage point, Andromeda appears so large that it was easy to believe that nothing could compare to its size. However, galaxies are immense systems, and their mass is intricately connected to the movements and distribution of stars, gas, dust, and dark matter within them. Pinpointing the precise mass of a galaxy requires sophisticated observational techniques and meticulous analysis, something that could not have been achieved in the 1700s or even the 1800s. This kind of knowledge calls for modern instruments, and we have only recently begun to truly understand the reality. A recent study has produced a new assessment of these beliefs. Scientists have slightly decreased their estimate of Andromeda's mass while simultaneously raising the figure for the Milky Way's mass. As a result, the current understanding is that the masses of these two cosmic giants are closer than previously thought. So, if you were observing from the top of Andromeda, you would see a galaxy just as huge. This perspective helps illustrate the colossal nature of the Milky Way. Despite its physical size, the exact dimensions of the Andromeda Galaxy are still the subject of ongoing research. Astronomers agree that, in large part, Andromeda's total size surpasses that of our own Milky Way, with a significant diameter of around 220,000 light-years. This exceeds the estimated diameter of the Milky Way, which is approximately 100,000 to 175,000 light-years, making Andromeda an important cosmic entity that resides in a vast region of space. This revised perspective also highlights the complexities and difficulties in accurately measuring the mass of galaxies. As we continue to study Andromeda and other galaxies, it becomes increasingly clear that our understanding of the cosmos is far from complete. The vastness of space, the complexity of galactic structures, and the ongoing discoveries through advanced telescopic technology challenge our perceptions of the universe. With the development of tools like the JWST, we are now able to look deeper into space and time, revealing details about galaxies, including Andromeda, that were previously beyond our reach. The study of Andromeda provides not only insight into the history of a neighboring galaxy but also crucial information about the broader mechanics of galaxy formation, evolution, and interaction. Andromeda's eventual collision with the Milky Way, predicted to happen in about 4 billion years, is a key event that will drastically alter the structure of both galaxies. This merging of galaxies, though distant in time, is an essential aspect of understanding how galaxies grow, interact, and evolve over cosmic timescales. Furthermore, the discovery of dark matter and its role in galaxy formation adds another layer of mystery and intrigue to our studies of Andromeda. The mass of Andromeda, like that of many galaxies, is thought to be significantly influenced by the presence of dark matter, an invisible substance that makes up a large portion of the universe's mass. Understanding the distribution of dark matter within Andromeda could provide new insights into the fundamental nature of matter and the forces that govern the cosmos. As new observations continue to come in, we may soon uncover more surprising aspects of Andromeda and its interactions with other galaxies in our local group. Each discovery challenges our understanding of the universe's structure and the history of cosmic events, contributing to a deeper understanding of our place within this vast and ever-expanding cosmos. In conclusion, the study of the Andromeda Galaxy has been pivotal in shaping our understanding of the universe. From the early observations by Al-Sufi to the groundbreaking work of Hubble, Messier, and modern astronomers using the JWST, Andromeda has played a crucial role in revealing the true scale and complexity of the cosmos. The ongoing exploration of Andromeda, as well as its eventual collision with the Milky Way, will undoubtedly continue to provide new insights into the nature of galaxies, the universe, and the fundamental forces that shape them. As we continue to study Andromeda and other galaxies, we are reminded of how much there is still to learn about the universe. Andromeda, with its rich history, complex structure, and looming future collision with our own galaxy, remains one of the most fascinating and important objects of study in the cosmos. Through continued exploration and technological advancements, our understanding of Andromeda, and the universe itself, will only grow deeper, helping us uncover the many mysteries that lie within the vast expanse of space. Galaxies that make up the core of the Andromeda Galaxy are impacted by a massive black hole. This black hole exerts a tremendously powerful gravitational pull on the nearby stars, causing these stars to move around the black hole in elliptical orbits, similar to the way planets move within our solar system's orbit around the Sun. At a specific location in their elliptical paths, the stars come closest to the black hole. This point is referred to as the perihelion. At this point, gravitational forces are at their strongest, causing the highest velocity of the stars, which speed up as they pile up close to the black hole. The stars release radiation in the form of energy, including visible light and additional radio frequency types. This increased level of concentration results in a bright star, observable in the region of the galactic core of Andromeda, which is known for its AGN, active galactic nucleus. The AGN is a highly active region in the middle of a galaxy, characterized by high emissions across various wavelengths, from radio to X-rays. The AGN that convert waves to X-rays are fueled by the presence of a supermassive black hole at the galaxy's core. These black holes are incredibly dense regions in space, where an enormous amount of mass is concentrated in a very small volume. Using cutting-edge telescopes like the Hubble Space Telescope, astronomers have observed a fascinating phenomenon in Andromeda's AGN. It appears to have 2 points of concentration, indicating that there are 2 distinct areas where light and other types of radiation are being released more intensely than in the surrounding regions. One of these points has some minor flaws, being offset from the true galactic center where the supermassive black hole resides. The mass of Andromeda's supermassive black hole is estimated to be between 1.1 and 2.3 billion solar masses, which means it weighs hundreds of millions of times more than the immense black hole in our Sun. It is believed that many galaxies, including our own Milky Way, have similar supermassive black holes at their centers. Because of this, supermassive black holes play a crucial role in the evolution and changes in the dynamics of galaxies. When matter like gas and stars approach a supermassive black hole too closely, it forms an accretion disk. The material in this disk gets hot and emits intense radiation across various wavelengths, which is why AGNs are highly luminous. Observations of the AGN in Andromeda reveal a particularly bright point of concentration near the central supermassive black hole. This feature is the result of unique interactions caused by gravity between the black hole and the stars that surround it. Andromeda also has another fascinating feature, an abundance of globular clusters. These star clusters are tightly packed groups of stars that orbit the galaxy's center, much like satellites revolving around a planet. It is estimated that Andromeda has around 460 of these dense, ancient clusters, each containing hundreds of thousands to millions of stars that came into existence around the same time. A staggering number of Andromeda's globular clusters provide valuable insights into its cosmic past, as well as interactions with smaller galaxies. Over billions of years, Andromeda has been absorbing smaller galaxies in a process known as galactic cannibalism. These smaller galaxies come within Andromeda's gravitational reach, and immense forces strip them of their stars and other parts. The stars in these cannibalized galaxies become part of Andromeda's stellar population, adding to the rich diversity of stars within the galaxy. This characteristic of accumulating globular clusters and absorbing stars from smaller galaxies is typical for spiral galaxies like Andromeda. Spiral galaxies, characterized by their disc-like shape with unique spiral arms, make for an ideal environment for combining and interacting with companions of lesser size. In addition to its other intriguing features, recent observations suggest that Andromeda may be going through a significant change. It appears to be transitioning from a typical spiral galaxy to a relatively rare type known as a ring galaxy. Ring galaxies are unique and extremely uncommon celestial objects characterized by their circular or elliptical ring-like structures. These rings consist of bright, young, blue stars, while the central region contains comparatively little luminosity. These distinctive features make ring galaxies stand out in the vast array of galactic structures. There are 3 main types of observed optical ring phenomena: nuclear rings, inner rings, and outer rings. Nuclear rings are located at the heart of a galaxy, while inner and outer rings are formed further out. Additionally, there are 2 primary types of ring galaxies, O-type and P-type. O-type ring galaxies have centrally located nuclei with smooth, regularly shaped rings, while P-type ring galaxies have off-center nuclei with rings that tend to have a more irregular shape. Ring galaxies are rare cosmic treasures, with approximately 1 in 10 galaxies classified as such. Astronomers have proposed 2 primary means by which they form. First, they can form through a galaxy collision, in which one galaxy passes through the center of another, triggering the formation of a ring-like structure. One well-known example of a ring galaxy formed through such a collision is the Cartwheel Galaxy. Andromeda and the Milky Way are on a collision course and will eventually merge to create an additional, even larger galaxy. This colossal event has already earned nicknames like Milkomeda or Mildruma, as it is known worldwide. However, while these nicknames are amusing, the repercussions of this merger for humanity remain uncertain. The eventual merger between the Andromeda Galaxy and the Milky Way is expected to dramatically reshape the 2 galaxies, creating an entirely new galactic structure. As the galaxies collide, stars within both galaxies will likely pass by each other without directly colliding due to the vast distances between them. However, the gravitational forces at play will lead to significant disruptions, including the formation of new stars, changes in the orbits of existing stars, and the possible triggering of bursts of star formation. The supermassive black holes at the centers of both galaxies will also likely merge, potentially creating an even more massive black hole. This merger is expected to occur in about 4.5 billion years, a timescale that is far beyond human lifetimes, but it will have a profound impact on the structure of the universe. The resulting galaxy could be an elliptical or irregular galaxy rather than the familiar spiral shape that both Andromeda and the Milky Way currently exhibit. The merged galaxy will likely contain a new distribution of stars, gas, and dust, as well as a supermassive black hole at its center, which may be surrounded by a hot, active region similar to the AGN found in Andromeda today. Additionally, the collision could result in the disruption of any planets orbiting stars in both galaxies. While stars themselves may not collide, their gravitational interactions could alter the orbits of planets, potentially leading to the destabilization of planetary systems. Some stars may be ejected from the newly formed galaxy, while others could find themselves in new and unexpected positions, orbiting around the merged supermassive black hole at the galaxy's center. Interestingly, as the two galaxies merge, smaller galaxies that are currently part of the local group, a collection of galaxies that includes both the Milky Way and Andromeda, could also be affected. Some may be absorbed into the larger galactic structure, while others might be ejected, further adding to the complexity of the galactic dynamics in the region. In the distant future, humanity may not be around to witness the dramatic event of the galactic merger, but through the study of current observations and simulations, astronomers are learning valuable lessons about the evolution of galaxies and the larger forces that shape the cosmos. The merger of the Milky Way and Andromeda serves as a reminder of the immense scale and complexity of the universe, and the ongoing interactions between galaxies will continue to influence the way we understand the forces that govern our universe. In conclusion, the collision of Andromeda and the Milky Way, while still billions of years away, is a key event that will reshape the structure of our local universe. It highlights the dynamic and ever-changing nature of the cosmos, reminding us that even the most stable and familiar structures, like our galaxy, are subject to the forces of gravity and time. The study of this collision provides valuable insights not only into the future of our galaxy but also into the evolution and fate of the universe as a whole.